is equal to, not exactly, not approximated, it is equal to, let me write, sum over n is equal to 0. Let me say that I have infinitely many such polynomials. I am putting infinity. Okay? And ask a question that I can write this as Cn includes un of x. Now I know what is Cn from here. Okay, I substitute it there. This is equal to so I substitute this here. This is equal to sum over n is equal to 0 to infinity. The Cn I will write it as integral minus infinity to infinity. I will write ul star of some x prime here because this is under the integration into f of x prime dx into un of x. Sorry, that is un. Yeah? Now I can write it in the following fashion. This is integral minus infinity to infinity sum over n is equal to 0 to infinity un star of x prime into un of x, because these are the two terms that depend on n, into f of x prime dx prime. Now remember, what is left hand side? No. So this is the same function. The same function is here. I have to get the same function instead of at x prime. I should get it at x. That's all. So when is that possible? You have to have the right function. That means this shows that this implies that this orthogonal functions 0 to infinity un of x prime un star of x prime and un of x have to be equal to delta of x prime. This is called completeness. Completeness. Any basis which exhibits this plus integral minus infinity to infinity un star of x into u del star of x ul of x dx as delta nl. This is called orthonormal. So if a basis which has orthonormality and also complete, we call a complete orthonormal basis. So if these two, this is the completeness relation, this is the orthonormal relation. If a basis has these two, then it is a complete orthonormal basis. Only then we can say a function can be represented equally as a linear combination of basis elements. So in quantum mechanics, most of the times you will come across this complete OMD, complete orthonormal basis. This is the word which every time you come across in quantum mechanics. When you say complete orthonormal basis, it means that you have a basis elements which satisfy this as well as this.
Why do you have to change that number of bases and number of coefficients?
If I don't, for any finite number of these things, this relation will not be satisfied.
Then cannot be such.
Yes. It will not be equal to
You cannot write equal as
equal. We cannot write equal.
You can go to the equal only if it is infinity.
Infinity.
The first equation is f of x can be by equal only if it is
The point I am trying to make is that Cn is equal to this is true even if it is not equal. If you approximate it, the Cn will be this. Okay, but if you make it infinite, that convergence property will allow you to say that it is equal. So equality requires infinite basis elements. And in quantum mechanics, it so happens that eigenvectors of every Hermitian matrix will form a complete orthonormal basis for the Hilbert space. So you can work with the eigenvectors of any Hermitian matrix as a basis. It will form a complete orthonormal basis. So any state can be expressed as a linear combination of eigenstates of any operator, any Hermitian operator. So physical observables are Hermitian operators. So Hermitian operators have eigenstates which will form a complete orthonormal basis of the inverse state space.
earlier when we discussed the